come and talk to our younger professional on the topic construction, digitalization, and natural fiber, building smart and building green. I've been introduced formally. I want to stay maybe for a disclaimer. I'm not into the construction. I'm into materials and material science. So what I'll be doing is I'll be looking at a material that will be used for construction. There's a research component to my talk, so I will try to focus on a material we all know, but it's just going to create a room for the research component, which for those of us in science and engineering will be able to try to explore, because we are going green, and that is what the world is all about, climate change and everything. AI has taken over, so we are going for digitalization. So this today talk is going to tell us about how these materials can also be used in space. So let's move on. What is construction digitalization? So this refers to integration and application of digital technology across all phases of the construction life cycle. So we talk about life cycle, we talk about from planning, design to execution, operation and maintenance. In like what I would tell my students, from cradle to grave, that is what life cycle is all about. So you talked about from the planning stage to the execution to the operation to every component of it to the end of that cycle. So what we talk about, or we'll be talking about, is integration and application of digital technology. So we'll be seeing how natural fiber can be integrated into construction and how that materials can also be part of the digitization component. So we are looking at how construction is conceived, built, and managed, making the entire process smarter, more efficient, safe, and more sustainable. So what are natural fibers? So natural fibers are materials that has a lot of application. They are biodegradable, which means they get degraded, unlike plastic that is causing a lot of pollution because of they don't degrade, which means these materials can grow. They can be buried, they can go back, they can disappear. They will decompose and degrade. They are lightweight compared to metals and every other materials. They are eco-friendly because they are green materials, because they are sustainable, and they have high strength. You will be surprised to know the strength of this material if you really goes into this science. And they are low cost. They are cheap and affordable. Where do they find application? Even in airplane. Yeah, for most of you, if you have flight with the Dreamliner is about 50-something% composite. But wherever you are in a plane next time, just take a look around. You see those beautiful aesthetics inside. You just tap on the panel beside you. They are plastics. They are not really plastic. They are fiber reinforced plastics, and those things contain fibers. And for building, which is where we are going to, for automobile, everybody has a car. There's one part I always used to explain to guys. I'll say, look, your bumper and your fender in the back, they are plastics. And they're not just plastics, they are fiber reinforced plastics. So they are these materials that you put fiber to improve their strength. That's why when there's a car accident, I think the first part that are good, but it reduces the weight and improve efficiency and reduce fuel consumption. And that was the idea of incorporating composite into plane. It gives more space. It has lightweight. It's eco-friendly. So natural fiber is a very versatile material for the future. And natural fiber, I just want to give us a brief of what natural fiber is. Natural fiber can be sourced from animals, from mineral. From the mineral is asbestos. Everybody knows asbestos, but asbestos is cancerous and is no longer used because of its negative influence. So for animals, it can be in form of wool, it can be in form of zinc. While for plant or vegetable, it's divided into 4 aspects. You can have from blast, which is flex, jute, trimsin, and knife. From leaf, you have ciacia, banana, abaca. From seed, you can get from cotton, capot, and cocoa is coconut. Then from wood, you can get the soft wood and the hardwood. So even for those of us already in construction, you see that wood is a natural fiber. So let's look at the sources of natural fiber. I just brought out this picture so that, because as we are talking about fibers, some people will be wondering, what are these fibers? So you can see from cotton fiber, this is coil from coconut. So when you see coconut, you see those fibers. And there's something unique about the coconut. I will tell people. If you look back to Menzies, Menzies over the years has a patent for their seat and their dashboard for those Menzies 180, Menzies 220, Menzies 280, all those models. They were made, the seats, the dashboard were made with coconut fiber that was collected from Congo. That was a patent for many years. No other manufacturer could ever use. So what they did was Menzies became the first industry or company that integrated natural fiber into automobile, and they use it successfully for years. While other cars were having issues with their internal doors, their seats, people will tell you, if you remember our fathers when we were young, those that have those Menzies V-Boots, 230, 200, the seat is always, no matter how old and tattered that car is, the seat doesn't compress. Those seats were made from coconut fiber. So we have other fiber. We have oil fan fiber, remix, flaps, canine fibers, and we see maize straw. We can have fibers from there. Then we look at the banana fibers. I think most of us, every day we eat banana. Bamboo is there. Pineapple is there. Palm fiber is there. Then among the wool we can get from sheep, we can get from goats, we can get from rabbits, and we can get for this wide range of animals. Those are the source of where we get this natural fiber. They are natural because they are not man-made and they're biodegradable. So I'll be focusing on bamboo for the sake of this lecture, because most of us are already used to bamboo, and bamboo has come. But I just need to emphasize here that research we are doing currently is replacing this already known with other available one. Like for example, I worked on my first PhD using plantain fiber. And for the first time, we took plantain from the stem. For those of us from West Africa, we know what plantain is. And I'm still currently working on that plantain fiber, bringing artificial intelligence for my current second PhD in mechanical engineering. So I'll be focusing on bamboo that is already currently being used so that we're able to see. But what we are doing in research now is we are using, because bamboo takes time to grow. Bamboo is not a plant you plant today and you harvest or you get the fiber tomorrow. But there are other plants like plantain that have started focusing on using. Is a cycle. You can get it within months to maturity. You harvest it, is a waste, and you get those stump, this stem, and that stem we can extract fibers out of it. So, but for the course of this lecture, I was just going to tell you, use bamboo as a particular case study. And but as we are going along, you understand that whatever bamboo is doing today, we are already bringing in other fibers, other natural fibers that can really do it. So bamboo is often called the green steel because of the 21st century, because of the remarkable strength, their renewability and versatility. They have been used for centuries in traditional architectures. Bamboo is the oldest. Even before we started using cement and bricks, bamboo for construction has already been existing. For application, you have bamboo for farming. They are using walls, roofs, scaffolding, in high-rise building. For engineers, we have laminated bamboo. Even as I'm talking to you, my stand, my phone stand, which was courtesy of University of Johannesburg, is made with bamboo laminate. So bamboo is already there. It is an ancient material, natural fiber that has been used for construction. So for non-structural component, bamboo has been used for partitioning, for wall flooring, wall cladding, for ceiling panel. You can see from this picture by our left, everything here is bamboo, which is what we used to. But if you look at the right, you see a more modernized one because technology, science and technology has come into place. And this is the old setting of bamboo. But as science is being developed, we have means of polishing them. We have means of embedding them in polymers and to get nice aesthetics and nice beauty out of it. So what you are seeing in both pictures are bamboo for interior application as a natural fiber. So for composite reinforcement, it is already known. You can see from this gentleman here, this is a reinforced concrete for, how do they call it, for a flooring, maybe for a high-rise building. And no, normally they use reinforced steel, but you can see they have used bamboo. It's not new. It's not an issue for, oh, can this thing? Oh, no, it's already there. It has been done. Buildings are already existing in part of Asia where these floor, high-rise building floors are already on bamboo. And you can see the bamboo mat. You can see a laminate. For example, if you see this laminate, you come across it, you won't really understand that this is bamboo. You must have gone into people's houses and you see these fluted panels for their interior decoration. These fluted panels are fiber reinforced polymer base with bamboo, and it has been done with other fibers, not just bamboo. But we are just using bamboo as our case study here. So you walk into a gentleman's apartment, you see these nice fluted wall panels. These are just bamboo and biopolymers that are used for this beautiful interior design. And those are what we call hybrid materials. So when you have two composite material, one is a continuous phase and one is a static phase. So polymers are being used to embed this bamboo and other fibers and have been used for interior decoration. And like I said, for concrete reinforcement, bamboo has already been used. Now let's look at digital tool empowering natural fibers in construction. What are the tools that has come into place for natural fibers when we talk about digitalization? So you look at building information modeling, which help architects and engineers to integrate natural fibers into the early stage design, considering the thermal, the aesthetic, and the structural properties. For finite element analysis, in one of our work recently, we are using finite element analysis. You all understand what modeling is all about. When we do modeling, we try to reduce cost. We try to replicate these materials in a real sense, and we use digital tools to test their property. Let's take, for example, the work I'm currently doing using finite element analysis. We developed this fiber reinforced composite using this banana, for example, that I said. We subject them into mechanical testing up to failure, and we use finite element analysis to see how the stress is being concentrated on this material. So I want to understand the point where the stress is being concentrated, and you'll be able to see the failure point of this material. So this digitalization has come to say we have the computational fluid dynamics. We simulate the mechanical behavior and efficiency of wood or panel for natural composition before the physical prototype are made. Now, let's take, for example, when I was doing my PhD, I was working on fiber reinforced, and I was trying to modify this fiber to improve the mechanical properties. Now, to be able to improve these mechanical properties, we understood the limitation of these materials. And because of the hydrophobic nature and the hydrophilic nature of both the polymers and the fibers, that they are not actually compatible. So we try to compat them, we try to do some modification. And we say, okay, let's do chemical modification, let's do physical modification, let's do this kind of modification. But in trying to do that, we have to come up with a design when we say, okay, if we put 1% of this, we put 2% of this, we put 3% of this, we produce the composite. So at the end of the day, we produce over 67 materials, different composites, then subjected all these materials into testing to be able to come up to say, okay, this is the one that has the best property. Even at the end of the day, the simulation tool will even be able to tell you that, no, you don't really need 2% of this, you need 1.8% of this. You don't really need 50% of this, you need 48% of this to be able to give. And that is why in my current study, in my second PhD, I'm bringing digitization, bringing artificial intelligence optimization to fiber reinforced, where we don't need to produce 1,000 samples to be able to say this is how we study and understand what the strength is. So before you make the actual physical prototype, you subject these materials to computational and digital tools for simulation. And that is where finite element analysis and computational fluid dynamics comes in. You can see from the structure of a building. So you're able to look at this material, you'll be able to simulate the mechanical properties, how this material will react to strong wind, how this material will react to. Remember, when you are doing construction, for example, you know where the sun sets, where the sun rises, and the materials at midday change in temperature, change in weather, and every other thing. So rather than producing tons of this material, you bring in digitalization to be able to simulate and be able to say, okay, well, let's do it this way, let's do that way. At the end of the day, you reduce. So instead of doing 97 samples, at the end of the day, you are just building 2 or 3 samples with a specific unique properties that you are looking for. So another type, like I just mentioned, is the AI component, which is what I'm working on. You talked about the machine learning model, which is used to predict strength of materials, insulation, biodegradability, the biodegradability, and the reinforcement of this material. Let's take, for example, what we have here. You see, this is a raw materials, and then I'm just going to put you through this stage of where this digitalization will come in fiber reinforced polymers, composite materials. For example, this is a matrix and this is a fiber. I want to bring this material together to be able to produce a fiber reinforced material. And at the end of this day, we want to look at the tensile strength, we want to look at the tensile modulus, we want to look at the flexural strength. Tensile strength is where this material is pulled from both ends. The modulus is the stiffness under that tension. Then we look at the flexural, we talk about flexibility, where this material is made flexible to maybe we can do it from 2 points, we can do it to 3 points. Then we look at the Young modulus, we look at the elastic modulus, we want to look at the density of the material, because of these materials, they are materials we need weight, we need lightweight. For example, cars were limited to certain speed in the base pass because these materials was made of steel, which had weight, and so they consume more fuel. Now we have a energy efficient car that are lightweight, that can run, they can accelerate fast. All is because these materials are made from lightweight. And what happens in a technical car, for example, is some cars up to 60% of interiors, some 80% of the interiors are all fiber reinforced polymers. The dashboard, that soft part from your steering, your door panels, the seat you are sitting on, those your jar, your roof, all these things are fiber reinforced polymers materials, and these materials are there. But before you use this material, you have to do a lot of mechanical testing. So let's use this for example. The next stage you go into is to put these materials and fiber together. Then you take this material to your, okay, normally when you do this material, you now say, okay, first and foremost, what is the ratio of fibers and matrix that must come together? You have to do that under a range. You can say, okay, let's have this metric alone. Let's put 5%, 10%, 15%, just like that, up to 80 or 90%. On the other hand, you can say, okay, but how do we improve the property strength of this material? Because this one is hydrophobic and this is hydrophilic. So for this material to be compatible, we need to create a material that will be able to bond together. And how do we do that? We can say, okay, we are going to use physical, we are going to use chemical, we are going to use biological method of modification. And under that method, you have to vary time, concentration. So you have a lot of data that you are trying to generate. But when you go into machine learning, you put these materials and you ask the machine to be able to do a deep learning where you're able to predict that for the tensile strength, you need this, that. For the modulus, you need this quality of the material. So you find a balance between them. And for the confirmation test, what we need to do is we just go to the lab and use the output from what the machine is telling us, what the digital machine is telling us, the AI, and produce a sample and run the analysis. And from already published work, which you can find in my profile at Google Scholar or Scope, you discover that we're able to get up to 96%. 96% validation. So which means there was a case where we put 5%, we put 10%, we put 15%. At the end of the day, the AI said you just need 12.5%. But we never thought about that because we took a multiple of 5, 10, 15, 20, which is normal for us. And he said, no, 12%. This one, instead of 20%, said, no, make it 18%. So by the time we got those data out, we went back to the lab, used, this is what the AI said. We put it into, and even the AI said, if you put it this way, this is the strength of this material you are going to arrive at. And by the time we got our own result, we discovered that our result was about 96% to what the AI is predicting. So for natural fibers in construction, instead of doing multiple samples, instead of doing trial and error, because building involves human life. When human comes there, they live there. So there's building collapse, or during winter, your building cannot uh, do things that you actually was designed for, then it becomes an issue. But when you bring in digitalization is able to modify these materials and be able to reduce cost and save energy and save time. So we have the digital twin in construction, which you can monitor the material degradation, because yes, there's absorption, there's structural stress. Those are some of the disadvantages of these materials. That's why we say before you put in natural fiber in any of these materials, we have to understand these materials. We have to understand their properties. We have to understand their disadvantage, and we have to come into a midst of modifying it. And now that we have done the modification, that is where we put it into application. But digitalization come to be able to monitor this material degradation. And we have predictive modeling, which can be able to tell us when replacement is scheduled. I think there is one culture we don't have in some part of Africa. We believe we have just done this thing and it should last forever. No, with digitalization, they'll be able to tell you at this particular time, you have to replace this. At this particular time, you have to replace this. At this particular time, you have to replace this. Then digital prototyping. Yes, before you go to actual production, you do prototype. And by the time you are able to say, okay, this, the, like what I said previously, when the AI said this is what we're going to do, we went back to do a prototype. And now we're doing the prototype, we validated it, it was 96% reality of what we got. So instead of building 67%, 67 samples, we do few samples, take it to AI under the machine learning training process. You train the machine, we'll be able to say, do just one. And when you do that one, you're able to see that even finally that one we produce had more strength than we initially got from our data analysis. So additive manufacturing, which is 3D printing, is also a way of, where at UJ we have already have a 3D printed house building at DFC, which was launched. And those filaments that are used for those type of printing, natural fibers can also be used as a reinforced, natural plastic reinforced can be used, has already been used. But the trick about these things, most of these fibers have already been used, and some of them have already been patented. So you just buy these materials without really understanding what those materials entails, because they are trying to protect, and the patent to protect them over a period of time. So additive manufacturing use the 3D printing. Some of those materials are already being used, produced with fiber reinforced plastic. So and those things will enable you to have material efficiency, and you have to design flexibility. When you are using polymer biocomposite in construction, you can do aesthetics with the finish. But when you are using metal, to get a smooth curve in metal is always difficult. You either do casting, you either do shaping, filing, and every other thing. But in polymer, you just get a mold and you're able to do it. Then you can do a rapid prototyping, and you can do on-site fabrication. Like our 3D building in DFC, it was an on-site. They didn't build it somewhere and brought down. It was here at the site. where this thing was being developed and this thing was being built. So additive manufacturing is also one digital tool that has been empowering natural fiber in construction. You can see from this sample, either a biofiber, you can use to produce filament. So what I explained here, these fiber are already included in what they use in producing this filament. What you do is you go to the market to buy this filament and use the filament to do your 3D printing. But fiber is already there. Remember what 3D is all about. Is a fast way of doing prototyping instead of building. Once you're able to get the design, you put it in a machine. It's a digital construction of a model or a sample. So we can do the smart chain supply. Yeah, most of you, that is your space in construction. You know what supply chain is all about, the blockchain technology. This can also be a system of tracking natural fiber materials from the farm to factory or to construction site. That is what blockchain is all about. And they always talk about it here at UJ that even our certificate has been integrated into the blockchain technology where you are able to actually monitor and track this material. So when the fiber is leaving the farm to the factory, you are able to monitor it from the factory to the construction site. You have to record the harvest location, the treatment method, because science has even proven to us that this material, for example, many years we focused on the Chinese bamboo. Everybody, the Chinese were already using it for centuries. Everybody was like, it's a Chinese farm bamboo. But by the time science was being explored, you have to understand the the breed, you have to understand the type of bamboo that has this specific, because they have different types of this material, different species. So we have to understand that, oh, is this particular species that has this property. And today that species of bamboo is even here in South Africa. So blockchain is part of those things that you're able to record the harvest location. Like I said, the treatment method, when you want to implement a treatment which is modifying, treatment is all about trying to modify and improve the property, the transport emission of bamboo fiber, for example. So ensure ethical sourcing. So when you say you want to avoid deforestation or exploitative labor, so neighboring material passport. So you can be able to select, for example, you just say we want to use the Chinese bamboo to be able to do our 3D printing or to do our greenhouse development. With the blockchain technology, UJ will be able to track the bamboo where it was being harvested in China, all through its harvesting, its location, until it gets to UJ to ensure that this contractor does not go and bring the Indian or the Pakistan version of the bamboo. And that is where blockchain digitalization comes into play. In conclusion, if you merge nature plus construction, you have a smarter future. When you bring natural fibers and digitalization, you have smart and sustainable construction. So you build green, you build smart. So in conclusion, I just put this together. I said, if you merge the wisdom of natural fiber with the power of construction digitalization, you can build not just greener building, but smarter and more sustainable future. Thank you very much for listening. I will be available for more questions.
Thank you very much, Dr. Patrick. Thank you for the lovely and insightful presentation. Honestly, it's a thought-provoking one. And in fact, my jotter is full. Thank you so much for this. Now we are at this question and answer section. If you have any question, please feel free to raise your hand and we'll recognize you. All right, Mr. Ekubo, you have the floor.
All right, thank you very much, Dr. Patrick, for a very beautiful presentation. Yeah, my question is, I want to ask, why is it that the adoption of these construction materials is slow, especially in Africa? You know, for instance, you go to a construction site, reinforced concrete, most of the time they use steel and all of that. And I understand that you've made some very important remarks with respect to that. So I want to know, why is it that it is slowly adopted, especially in Africa? Thank you very much.
All right. Probably I take all the questions and I just try to answer them. Or is just one question that is available right now?
Okay, any other question? Please, you can go ahead and answer him so we
Okay,
can,
let
while
me
we're
take those
waiting for
questions. You
others.
see, one of the challenge we have in, let me put Africa, is standardization. There is, when you people, the construction people will be having their conference in September. I sent in a paper where I did talk about this natural fiber in a green building. Is one of the paper I will be presenting in that conference. And one of the things is, if there is no standardization, then there is no adoption. For example, if you want to buy a steel, you already know the composition of that steel. You already know, uh, the component. You already know the parameters. Let's say, for example, go to buy this material for research. Already, Merrick or whoever will tell you this material contains this percentage that, there's a standard. And like in material characterization, we have the American standard of testing and measurement, which is ASTM. We have the IOS standard. So there's actually no real standardization for this now. And that's why we are having this challenge. Because I was just, there was something, characterization I will share with you when I was back home in Nigeria. There was this building they were building inside our complex, and since it was an engineering institute, when the material they come to R&D, and I was in polymers. I was heading that small unit to do those material characterization. Now, one thing was very fascinating. They brought in iron rod about 25 or 20 something very heavy rod. And the architect was like, no, this rod is going to add more weight to this house. This place is already a swamping area, and we have pillars and this scriptation. I will just let do of 12 And the contractor was like, no, this is a federal government building. The quantity surveyor quoted for us was we use this 20 rod or 20 something rod. So while the argument was going, my other department was like, okay, you said you need it for strength. You said 12 can do it. Let's take this material to the R&D and do a research. And everybody should please listen, because this change a lot about me, my understanding about science and the rest. Now, for us to be able to do those analysis, we must prepare those samples according to the international standard, not according to their sizes. So let's take, for example, a composite material. You have to be double size. It must be 133 it must be 5 thickness. You understand? The middle grip area must be this So we prepared both the 12 and that mighty 24 or 20 something rod into the same dumbbell shape that American Standard for Testing and Measurement says this is how a steel should be prepared. Whole and behold, when we took this material to the lab, the result came out. The 12 has more strength than that 20. That 20 something was made from recycled metal. Why that 12 was bought, because the architect ordered it directly from Ajakuta Steel. Why this one, only God knows where he bought it. He bought it from this local vendor. So he was looking at the size of this metal, while the architect was looking at the strength of the material. We took this material to the lab. We discovered that when you bring them down to the same size of testing materials, you discover that whole and behold. For example, carbon nanotube. If you Google it, you can just pick your phone and Google it, strength of carbon nanotube. They will tell you carbon nanotube is even stronger than the strength of a steel. But let me shock you, when you see carbon nanotube in your eyes, they are just like powder. Nanotube, the first time I saw nanotube, I just put them on my hand, in my glove. I was like, how is this thing stronger than steel? So there is no standardization for this construction material. That is what we're having challenging. So when we are doing this actual building, like which a developer work does, when material come to the site, they quickly take a part of the material, for testing, and because they have a particular standard that this material must meet. So if we have the standard, like say, for example, when I talk about the blockchain, for example, I said with blockchain, you can monitor the bamboo that you are bringing from China to UJ to do a particular work, because there's a particular species of bamboo from China. It takes about 5 years. When you plant that bamboo, for the first 5 years, it's growing downward. So it doesn't even grow upward, it grows downward. Then after that first 5 years, before it starts growing upward. That particular species of bamboo has, so they call it the steel. So if, for example, you order that type of bamboo, then one contractor will just go to Pakistan or to Lebanon and bring a bamboo from that place. And bamboo is bamboo, you are looking at it, then you do your construction. Even when digitalization says this building is supposed to start to 20 years before this thing will be placed, within 10, 15 years, it goes and they start blaming global climate change. So, but with digitalization in the construction, which is what we are talking about, blockchain will be able to monitor, to be able to show this bamboo came from this particular farm, not even this country. First and foremost, it came from this farm, whether it's being transported, whatever it goes through immigration, through custom, or wherever it's going, they are going to do a kind of a follow-up to be able to show that this materials was not swapped or was not changed and it came from its origin. So to answer your question, the problem we have is because there is no standardization. And in construction, thank God we are in a digital era. What we understand and what the essence I gained from that project was, when material comes to the site, what we do is to take example. When I was working in Michelin, for example, I worked with Michelin, and our job there was to produce the polymer that was used for plane tires. Specifically, it was used for producing plane. So at every point in time, we take sample from every sample, every batch. We take sample, prepare that sample, we run down to the QR, quality control lab, and do the analysis. So by the time that sample goes to the final stage of production, the result is back, and if the result shows that this sample does not meet the specific standard, it goes back into recycle. So if there is standardization, we'll be able to use materials, especially for West Africa region, and have no challenges. Thank you.
Thank you very much, sir. We have Mr. Fortune on the line. You have the floor, Mr. Fortune.
Thank you, Mr. Moderator. Thank you, the guest speaker. There's something you just said that's really got to me. Like, you gave a scenario that they brought two different thickness of steel, and then they found out that the lesser one was better than the other one with a higher thickness. I mean, this calls for I don't know, what's the role. I want to just put it this way: what's the role of digitalization in solving these kind of issues that will be arising in, and I think this is happening so much in many construction sites, and people are not just aware. They just bring the material and they just start using it. My second question is, what is the role of cannabis in the future of construction? Thank you.
All right, thank you very much, Mr. Fortune, for that thoughtful insight. I will answer this question from my usual way of telling nice stories to illustrate this point. I was listening to a professor of architect who was doing an inaugural lecture, and he were talking about building in sub-Saharan Africa, where we came from. When we get to 5-story building, this building start collapsing. And in the developed world, they build 20-story buildings, 50-story buildings, and these buildings are standing the strong wind and the rest. And he made a point about something. He said, at times, the load we put on the upper floor does not even warrant it. And he took us through how some skyscrapers are being constructed. That from the base, to the 5th, 20 or 60 floors where it's going to be is all about pillars and floors. They put those pillars, reinforced pillars, they put the floors. And later they start putting those partitionings. And he was trying to make a case that you put so much load in trying to, must you use a 9 mm bricks to partition a building? Let me take UJ for example. If you look at most places like our office, where we have B3, 101, 102, you get to the office, everything is nice, everything is looking furnished. My dear, all those partitions are fiber reinforced. They are not 9 mm thick brick wall because these are loads. So when we talk about digitalization in construction, instead of putting, just like we did from this, instead of putting a 20 mm rod, which is adding more load, not strength. For example, I went as a student, I won a prize as a best polymer student for a project. They were talking about a footmat. I constructed a footmat using the shaft of rice as a reinforcement. There was a place close to my school where was a rice mill. So every day we go, we pass through that rice mill, and you see those rice shafts are just being packed. So one day in class, I asked our lecturer, and I'll say, these are fibers. And he said, yes, you can put in the material. Then when we did formulation and compounding, we got to understand that for every material, for every stage of building or construction, or whatever you are doing, you must understand the strength, the mechanical requirement of that place. For example, when we talk about this building, what does the wall panels, what does the wall do when you partition rooms? Is it a studio that you want noise absorber, the acoustic property materials? But some people will just put a 9 mm concrete block just to partition a room. And at the end of the day, they put an air condition for coolness and things like that. You don't really need that because there is no digitalization. There's no, you have not been able to put this material into digital form for them to be able to predict and tell you that this is what you actually need that material for. So what I did at the end of the day, I used that rise ox to create a footmat. I modify it and I have the mechanical properties. When we got to the conference, I was just a second year student or a third year, yeah, second going to my third year. So when I got to the conference, all these guys from University of Lagos, they were there. I was scheduled to be the last. Before I could even finish speaking, they called me to the auditorium. They said they have already seen my project. I just have 10 minutes to talk because nobody took it serious. Okay, I'm giving 10 minutes. So 10 minutes, instead of talking much, I just opened my bag. I brought out a footmat, and I went to the chairman of the panel. I said, can you please take this and let everybody have a feel of it while I do the talking? And then he touched it, he passed it around. They gave me 10 minutes, but for 30 minutes, I was still talking because everybody was passing it around. So by the time it got to the point where it was question and answer, then everybody put on there, this chairman have to stand up and came beside me and said, I'm going to help you, young man. Everybody's interested. At the end of the day, what was it? What is the average weight of a human being? Average 100 kg. We subjected this material to mechanical testing after reinforcement. Discovered that this material can withstand an abrasion resistance from 120. So you don't need a metal steel or a carbon fiber to reinforce the polymer you want to use for a footmat because your carbon fiber will give a strength of above 500. Meanwhile, the average human being is just 100. So people don't even weigh up to 100. So we said averagely 100. Now you can get this shaft of rice that is lying down in the rice mill and integrate it, you modernize it, you you do a chemical modification treatment, you put it into this polymer and you produce this nice, you produce a footmat exactly how a footmat is. The only thing we told them from the pictures and everything, at first they will not believe anyway when you say this material contains this. So at the end of the day, why we use this? Because you must understand that the strength of using a carbon to do this material is this, but if we use this, what is that? So the same way, like we said, the architect said, we just need this is the megapascal per kg of strength we need for this material. The tensile strength must be this, the flexural strength must be this, the tensile modulus must be this, this modulus must be this. And this guy believes that having a very thick 20 rod can achieve that. But the intelligent, smart digital architect said, no, we are looking at the strength of the material, not the size of the material. So with digitalization, we look at what are the parameters are you looking at. For example, you say you are looking at beauty. Let me bring this picture, for example, interior of a house. You are looking for beauty. Look at this beautiful house, but it's fiber reinforced. This is the one we have, the model, the previous one, when digitalization did not come into place. But now with digitalization and modelization, this is what comes into play. So whether I like it or not, digitalization has come into construction and come into every part, just like artificial intelligence has come into every part. Artificial intelligence is used by men to make life better. So with that modernization, there cannot be 21st century construction without digitalization. If you look at these two pictures, for example, what we know about having bamboo or having fiber in the city room is what you have by your left. But with digitalization, what we know is what we have by the right. And even sitting in my table, I have a phone holder charging is made of, and it's written there, research capacity development, courtesy of postgraduate school, made of bamboo. And it's there. So digitalization has come, and that is why the world is training top guys like you who are in school studying, probably mostly at a postgraduate level, and integrating digitalization into this. The next thing we'll talk about is the cannabis, for example. Cannabis, let me go back to type of fiber. We already have M as fiber. And this is one area, thank God you brought it. This is one area I'm actually looking for collaboration, because this material from other parts of the world has been used. When I came down to South Africa, for example, I discovered that, look at M, for example. I saw this, there was even a plant inside campus. I saw this plant on campus just today. And I stood there and I was looking, I said, this is hemp. I said, well, it's legalized here. But South Africa is the only country I've been to in Africa that legalized hemp, cannabis. But there is no data of the fibers from that usage and application. And I try to, in the construction conference upcoming, I will be able to try to make a case of that, see if I can get collaborators, if I can get researchers who will be interested in that aspect. For the first time, we'll be able to say this is South Africa cannabis fiber. This is how the structure looks like. If you look at all these fibers in scanning electron microscope, you will see there was a PhD student then, when I was still doing my master's, who took a sample abroad. They brought the sample and they missed the labeling. So the guy was so confused. So, and my prof said, oh, Patrick is very good in natural fiber. He has worked with natural fiber his life from undergraduate. So the guy came, when he brought it, I separated. So he have already sent them an email for correction, because let's say, for example, you are sending your sample abroad, you label them XA1, XA2, XA3. When they are running that analysis, they want to save XA1. The system tells them there's already an XA1 saved inside the system. So you have to use another name. So probably the person now decided to use a different name to save, but he probably wrote it down somewhere. So, but when he sent the result, the guys got that what I say is X, they should make SA1. I'm seeing WW1. So he doesn't even know. But looking at those scan electron microscope of those fiber, because he worked with coconut fiber and palm fiber, I was able to separate all the fibers for him. And when they now sent him an email to reply and said, yes, we changed the code. Your XA1 is now XA2. It's now WW2. He was able to see that. Then he met me again. I said, how do you know these fibers? I said, if you have studied these fibers for long, you'll be able to know that research has been done and they have been able to view the surface of this material at scanning electron microscope level to see how the structure, but we don't have anything, absolute anything about cannabis from South Africa. And that is an area of research I will be looking for collaboration with anybody who's interested. We can be able to come out with that fiber structure, morphology, characterization of that fiber. Then before we move to the next step of applying that fiber into different polymers and seeing their strength. We might not have bamboo in space tomorrow. They're talking about space science. Bamboo might not grow in space. We eat banana every day. There's banana fibers every year. We don't eat bamboo. People might not be able to wait for 3 years, 4 years, 5 years for bamboo to mature. But your banana, your cannabis, those are crops that, your pineapple, for example, those are crops that grow within a short period of time. And those fibers will be available to be able to do a lot of research work. So thank you for making mention of that cannabis from South Africa. We'll be looking for collaborator. Is a future work that we really need to do. It has been on my mind, and I'm still waiting for an opportunity to explore into that route. Thank you very much.
Yeah, thank you very much, Doc. We have Swadini, you're welcome. You have the floor. I think you are muted. All right. Then we have Upereg on raising his hand. Please, you're welcome. You have the floor. Uperege, please, you have the floor.
Hello?
We can hear you.
Hello.
Go ahead.
Yeah, we can hear you, but it's
Okay.
very low.
Good evening.
Good evening. We can hear you, but it's very, very low. Can you please increase the volume?
Yeah, I was saying with these materials, they are very good initiatives in terms of saving weight. However, I've been involved in the fire engineering perspective for several years, and I'm just shaking a bit in terms of we could maybe design a material and it performs well structurally. But when it comes to the fire engineering analysis or engineering of that particular structure, it might possess different results when exposed to the fire scenarios, even though it might be good on the mechanical or structural parts. So I'm not sure how the collaboration between the design, the mechanical, as well as the guys who are dealing with the standards to ensure that while there is improvement in all these materials, it is a consolidated effort, even to the guys who are publishing the standards, to ensure that as these materials are coming into the equation, we don't only focus only on the structural and mechanical side of things, but also other impacts that will affect the building operating at large. Thank you.
All right, thank you very much, Mr. Tusiyeni. I don't know if I got it right. Now, let me give you a rundown of how materials is being done. When you have a material, for example, the research component of this material is first and foremost, you have to look at applications. Application is a very vital, there is a work of ours that features in UJ magazine in 2022, 2021, 2022, after the what they call it, after COVID. What we did in that work was we used plantain fiber. We added carbon nanotube to improve the impact strength. I would recommended the application for automobile application. The interior of the car door, the fender, the bumper, the rope cover, the lining of the boot, those were materials. So let's say, for example, you have a material you want to be able to study what are the areas that this material will be applicable. You look at the mechanical strength. If it's outdoor, you look at if it's outdoor, you look at the fire, you look at the weather, you look at water absorption, you look at the weight of the material in relation to the density, you look at the biodegradability of this material, you look at the weather. There are some polymers we subjected to weather condition. Leave them in the open for seasons, winter, spring, summer, then we'll run the analysis again, we'll compare it, and from there we're able to monitor the degradation of this. Now, for example, when we did alkaline treatment, one of the professors who came for construction said, when they finish constructing, maybe building a concrete floor, why do they keep adding water? They just spray water on it. We have seen in the local construction site, they just spray water on it, they just spray water on it. People are like to prevent crack, to prevent it. So the guy was trying to explain that because of the component of cement, which has a high level of something carbonate on the rest, say the more addition of water that it goes as it cures, because it's a process of curing, it adding up that materials, it adding up. Just like, for example, if you, okay, let's use pap, for example. When you turn your pap, is soft and floppy, just allow it to cool for 5-10 minutes. The more it gets cold, the more hardened it becomes. So when you are doing this material, you don't just say for structural application. Let's say, for example, the indoor application, you want to use it for beautification, your polymers, and you don't need more strength, you don't need this, you don't need that. Or what you need, you just focus on this is its area of application. So we are going to apply it in this area. What are the properties that are necessary for it? If you are going to apply for this area, what are the so if you are going to apply for an area where there is going to be fire, let's say, for example, you cannot build a house without using wood for the roof, for example. And we all know that when fire gets to the roof, they will tell you the house is already completely burnt, because the roof, we have not been able to replace the roof of building except with metal steel. With wood, the conventional house we are living in still carries wood. So the area of application, final area of applications will also indicate the area of there are some polymers, fiber reinforced polymer, which are subject to impact. We focus more on the impact. We compromise the tensile, the flexural for the impact because of the areas of application. There are some areas you compromise. This one is this. So when you do a lot of sample, you try to modify the percentage treatment, the percentage of this, percentage of that. Remember, they can still be hybrid, where you bring this polymer, you bring this fiber, you bring this fiber. We do hybrid, you bring it 2-3 fibers together, and you do this property. You're able to say, okay, for this, we are looking at the water absorption property, that this material will be used outside. And we just, okay, like in my office, for example, UJ is made up of fiber board. What is the fiber board there for? It is not, impact strength is not one of it. Whether water absorption and sustainability is what that material is all about. That material is not there because of impact strength. A truck is not going to run through my office to break that door. So I understand your concern about fire or whatever, but whatever the factor of where it applies. So when we are designing material, we always look, that's where digitalization still comes into play. What are the application of this material? If this material is going to be applied for this purpose, what are the strengths you are going to look out for it? So when you do that, you do all your analysis and you focus on improving. And remember, if, for example, you are looking at tensile, for example, and you have a higher impact strength, you can be able to say, okay, let me improve this by adding a nanoparticles. Let me improve this by adding this into the material so that the tensile strength will become greater than the impact strength, because where this material is going to be used, we need more of a structural strength rather than an impact strength. So that's how we find the balance between those things. So digitalization also come into place in trying to find a balance about the final application of these materials, so that you'll be able to know how you're able to modify this material for final use. I hope I'll be able to answer that question.
Thank you very much, Dr. Patrick. We have a question here from Aliu. It says, thank you so much, Dr. Musili, for the impactful lecture. Can we make use of melon shell, because we have a lot in Nigeria which waste away?
Wow, thank you very much about that. You see, in areas like Nigeria, Ghana, West Africa, we have a lot of materials that we can use for research. But remember, in that area, we don't have funding. I'm currently working on still using plantain fiber in digitalization and AI for a PhD. I have to go back to Nigeria to get plantain fiber because here what they have is banana, and I don't need banana. I need plantain because it's specific. It's specific. Banana and plantain are two different things. So melon share is, in fact, there was a student who wanted to work on it, but he was having challenge with funding. So he just wanted to produce a composite. He didn't want to modify. He didn't want to do some kind of modification, treatment, processing, looking at physical modification, chemical modification, and biomodification to be able to do this because he doesn't have funding. So if we have opportunity of getting some of those materials, these are materials for master student, PhD student can work on it. We bring those materials. We can even use it in reinforcement of concrete. Yes, it can be there in concrete reinforcement. We can carbonize it and add it. You see, there are a lot of things you can do in the construction. We can improve the strength of material for concrete. They are already putting fibers into concrete. In Nigeria, we have sachet, we call it pure water. The guys from Nigeria, Ghana, Togo will understand what pure water is all about. Those polymers are now being used in bitumen for road construction. Those material can also go for concrete building because they are waterproof. So there's a lot of opportunities opening where you can even bring in master student, PhD student to work on it and say, work on melon shell, for example. Let's get somebody from my space, which is material science. Let's look at that melon. We modify it. We structure it. We look at the crystallographic parameter. We look at the chemical parameters. Then we'll say, okay, let's put it into polymer for green building. Let's put it into concrete for concrete building. Let's see the strength of this material and compare it to the already existing ones. Then we can now find a place to apply it. Sometimes you just have a concrete in the middle of the road where you put a sandboard. That is what is just there for it. It's not carrying load, it's not carrying weight, it's not. So application determines some of these materials. Like I use the footmat, for example. Footmat is being made with a material that doesn't really need to be there and it's making the price to be very expensive. But when we brought this agricultural waste into it and put it in the back of our mind that the average weight of somebody is 100, we'll be able to produce material and it works that way. So thank you very much. In fact, I've jotted it down. It's something we can get those materials from West Africa, break it down here, I'll be able to do it. So thank you very much. I hope I'll be able to answer that question.
Thank you very much, Doc. Do we have any other question? Okay. Let me just quickly ask my own question. Sorry, on the average, sir, what is the life cycle of this fiber, like bamboo, for instance, in construction?
The life cycle of this material actually depends on the application. Where this material has been applied for. Let's take, for example, you might have a plastic bucket in your house, which you use in bathing, just in your bathroom. That plastic bucket can be there for years, 2 years, 3 years, 4 years. Then at the back of your house in conventional Nigeria, for example, you have this plastic bowl you keep outside for rain to gather water. Here we gather water during the rainy season in Sub-Saharan Africa because of shortage of water. You discover that bucket outside, that one outside, within a year, it lose color, it start peeling. When you carry it, it start breaking. Now, because that one is exposed to outdoor, where there's UV, there's light, there's this, and that other one is just there in your bathroom. The only thing that one is there in your bathroom is carrying water, maybe warm water. You can never put a boiled water into it. So the area you use to apply it after, that's where digitalization still come into place. Digitalization will be able to tell you that the life cycle of this material, if I'm going to use it for concrete, is going to be this. The life cycle of this material we're going to use for outdoor application is going to be this. Now, for example, we are using ties. There are wooden ties, bamboo ties that people are using. My sister's house, for example, the kids, they have their own sitting room and playroom. The playroom is made of bamboo ties. They imported the ties from China or something like that. It's not our normal ties where we jump on top and get. It's wooden. It was laid just the way they do normal ties and stuff like that. But it's indoor application. And they have been living there for the past 8 years. But because it's the children's room, but you cannot put that tie in a walkway or in the front of the house because it's been exposed to weather condition. And remember, children room, these are children, the average weight of a child is still between 0 to 20, 30 kg and stuff like that. So wherever you're going to do the application of this material, that's where the most important where digitalization comes. So at the end of the day, we're able to see, when you're able to, for example, this melon share we just talked about, if you put this melon share, for example, into research and say, okay, from our data, this is the strength, in water absorption, this is the percentage. In impact, this is the percentage. Then we now look at where can this thing be applicable. At the end of the day, you say, okay, for green building, we can just use this to do ceiling. For green building, we can use it to do internal door frame. For this building, we can use it to do fluted wall panels for interior design. In this, we can be able to use it to do picture frames. We can use it to do interior design. For this, it can only be applicable in the bathroom and stuff like that. So at the end of the day, your application becomes the norm after doing this research to say this material. You don't need a steel table. You don't need a steel wall plan panel. You need a fiber reinforced plastic panel. And fiber reinforced, it reduces weight, it reduces cost, it's lightweight, and it's biodegradable, climate change, and it's green. So we put all these things together to be able to make our choice. Thank you.
Thank you very much, sir. Please, any other question? All right. Okay. Mr. Dr. Do, you have the floor, sir.
Okay, thank you very much. Doctor, I want to really appreciate you for that insightful presentation. My question is this: there was something I stumbled on online sometimes. It was about these bamboo reinforcements. I don't know how sustainable it is and how resilient it is in terms of construction.
What exactly is the question now?
Yeah, I saw it online. Bamboo are being used in lieu of reinforcement. Instead of reinforcement, they used bamboo. All these bamboo props as reinforcement. So I want to ask if it's sustainable and if it can actually do the work of a reinforcement.
Yeah, it can. It has been used. I don't know if okay. Let me share my screen again and show you. Let me share my screen and show you something. I think you are talking about something like this. Type of concrete reinforcement.
Yes.
Is that what you're talking about?
Yes.
Now it has been used. It's not new. It has been used. The problem we have, thank God we are in a society now. Before now, nobody knows about life cycle. We think anything we do is supposed to last forever. Recently, we were trying to do lithium-ion batteries and looking at the efficiency of this battery and the rest. And you'll be shocked that even the manufacturer will tell you there was a bulb, they told us the number of days the bulb is supposed to last. An LCD bulb, you said it can last for 3,000 hours. So whether you put it on for 6 to 8, you put it off, the next day again, you put it 6 to 8 again. So one day you just see that light will just go off because the life cycle of that life has already been programmed for 3,000 hours. You understand? So at times we don't even know because some of these guys in sub-Saharan Africa, they just go to China, they import this material, they just put people say, no, this product doesn't last, this product lasts. Everything has a lifespan. And that is what life cycle assessment is all about. And that is what digitalization is all about. The life cycle will be able to tell you this material is supposed to last from this to this. So when we talk about these buildings and the rest, we actually want building that lasts forever, forgetting that sometimes this building have to go for renovations. This building is supposed to last for a particular purpose. Or let's take, for example, you want to build a game village for a sporting game or whatever. You know that, okay, after 10 years, we are going to rehost. So after 10 years, this building should be remodified. This building should be reconstructed, or this thing should go. So each of those materials, every materials have a life cycle. The problem we have, because there was no digitalization, we thought they will last forever. Nothing was designed to last forever. And that is why people have now studied, people are now specialists in life cycle assessment. There was a particular time when I just came to UJ, one of our lecture theater, they were pulling it down. They were removing the rug, they were pulling out the chairs, and this thing was nice. So I was telling my prof, I said, no, nothing is wrong with this thing. He laughed and he said, part of the contract is after a particular year, everything will be put down and replaced. But coming from sub-Saharan Africa, we just put this thing there forever. Even the roads we are using, the road have a life cycle. That's why at a particular point, you just see potholes coming up and the rest. And that is what construction is supposed to do. At the end of the day, construction digitalization, you're able to say from our profile, from our standard, we are building this, but this is a life cycle. That's why every project now has a life cycle assessment. So if you are using steel and the life cycle of this project is supposed to be 20 years, and you are using bamboo and the life cycle is going to be 20 years, bamboo is cheaper, is lightweight, is green. Why are we not going to use the bamboo? When we talk about climate change and the rest. So if we understand what digitalization is all about and we start implementing it in the construction, we'll be able to see. The problem we have as Africans or from sub-Saharan Africa, we believe that whatever we build is supposed to last forever, which actually is not the case, because there's always a life cycle of every material, even the metal steel. Some of the metal steel, like what I said initially, for digital construction, when material come into site, samples are supposed to have been run, or the contractor is bringing this sample, is bringing this material with a data. Like those of us, my background is in chemistry, industrial chemistry, because I do much of mechanical, industrial, and chemistry. When we buy chemicals, it comes with a data sheet, because standard has already telling us. The data sheet, there was a time I was in the office, they brought a chemical and they had to start working. I said, I need time to study the data sheet. And my other department was, what are you talking about? This work is urgent. I said, there's no when it comes to life and then give us 24 hours, let's study this data sheet. And the following morning we came, we said, no, we have to do this, that. And they said, well, I said, because the data sheet said, whoever is working on this thing should not be on this thing for more than 48 hours, because he will feel dizzy, he will do this due to the inhalation of this chemical. If he's going to use nose mask, even when using a nose mask, he must not exceed this. So they were shocked. So that is what construction everything is supposed to come. Somebody is supplying steel rods to the site. He should be able to tell you the tensile strength of this steel rod is this. The flexural strength of this steel rod is this. The modulus of this material is this. For this project, this is the life cycle of this material from cradle to grave. So when you have this, what digitalization is all about, and you monitor it, you'll be able to have a perfect construction. You might have wondered why are buildings collapsing in sub-Saharan Africa and buildings are not collapsing here, and you have typhoon, you have weather, extreme weather, and the buildings are standing. Why in sub-Saharan Africa, we just have rain and sunlight and buildings are collapsing? And this is because there is no actual standardization to be able to understand that every material have a life cycle. Sometimes when the materials even coming to the site, it's almost at the end of its life cycle. Some of those metal rod, those iron rod have been out of the factory for the past 10 years, sitting in someone's shop. And you know what those guys do? They buy rod. By the time they finish, they are selling. There are still some at the base, they bring fresh one on top. Some at the base, they bring fresh one on top. Some at the base, they bring fresh one on top. One day, after 5-7 years, I'm going to sell that one on the base. That one has already gone 5 years of its life cycle. Even with that being used, because already it's exposed to weather, it's exposed to already extreme condition. And now you put that inside concrete and you don't know the life cycle of that materials, and you start having cracks. You wake up one day, you start seeing cracks everywhere. And there's theory about why you're having cracks, but most of the time it's because these materials are already exceeding their life cycle.
Thank you very much, sir. Please, for those that have questions, you can check the chat box and you can send an email to our doctor. He's willing and able to answer any questions, and is also open for collaboration. All right. I really want to appreciate everyone for staying till now. I want to appreciate us despite, I want to especially appreciate our guest speaker. Despite his busy schedule, he actually gave us his time and allowed us to enjoy from his pool of knowledge. In fact, my own take home tonight is this: natural fiber plus digitalization equals to smart. So I really appreciate you for this wonderful section. Thank you so much, sir. And we hope that when next we call upon you, you will answer us. Thank
My
you very much,
pleasure.
sir.
I'll always be
Yeah.
available.
All right,
I'll be
sir.
available for. I will also be available for collaboration. For those of you in the digital space, you can start looking at green materials because actually the world is going green. Climate change, the world is going green. So it's better we start looking at that direction and see how we can improve the strength of concrete, how we can improve the strength of materials. Bringing waste is one area of research that we still have to bring waste material into it, bring other fibers that have not really bamboo. Bamboo takes time to grow, but there are other ones that we can chemically modify, we can physically modify, and we bring it into these materials, and we get materials that we can use in the construction. So thank you very much, everybody. My email is down there. You can reach me for collaborations and for further questions. I will be able to respond to you. And I thank Mr. Fortune for the opportunity. And I'll be available. You call upon me because it was interesting for me anyway, having this construction space. So thank you very much, everybody.
Thank you, sir, and God bless you.
Thank you and good night, everyone.
Good night, everyone. See you again.
Thank you. Cheers. Bye.